So we got a fairly steep ramp this time, 60 degrees. And the box is sliding down this ramp. And the coefficient of friction is given. We have to determine the acceleration. So it is going down the ramp. This is the velocity. That's important to know because the friction is going to be in the opposite direction. Okay, so I'll start with the free body diagram. Actually, I should define my direction vectors here. So x will be down the ramp, and y will be perpendicular to that. All right, gravity, straight down. And draw the perpendicular components for that. Normal force is going to be perpendicular and matching the y component of gravity. So I'll use tick marks. And then friction. So here's an issue. I don't actually know which way the acceleration is. It does not say. Remember, which way it's moving is different than which way it's accelerating. So I don't know if I should draw friction longer or shorter than the x component of gravity. So I'll draw something that's fairly close, so it's hard to tell. But I actually don't know which one is bigger in this case. Okay, I do know that the normal force is equal to the y component of gravity, though. In terms of the x component, since I don't know which one's bigger than the other, I can't exactly use the magnitude method, so I'm just going to have to go with full vectors here. So the net force will equal to the sum of them. So Fgx going in the x direction plus the force of friction, which is actually going in the negative x direction. Okay. So then to calculate the acceleration, I'm going to have to change F net to ma. I'm going to also change the Fgx and Fgy's to mg, to their component formulas. So mg sine theta for the x component, and mg cos theta for the y component. And then lastly, I'm also going to change friction to, well, it's going to be minus mu normal. So that formula gives the magnitude for friction. But I know it's in the negative x direction because it's going to be opposite to the way it's sliding. So that's why it's a minus sign there. Okay, so what I'm going to do is call the left formula, formula 1. That formula, it gives me another way to express normal force, basically. And I'm going to actually substitute that where I see normal force in equation 2. So basically right there, we're going to change that to the expression from equation 1. So this is called a substitution step. So I'll say sub 1 into 2. Okay, so I'm going to need a lot of space here. So that's going to turn into ma equals mg sine theta minus mu. Now the substitution, so normal force changes to mg cos theta. surround this whole side in brackets and write the x direction there. So whatever I calculate inside that bracket, that will, if that's positive, then that means it's going to accelerate up the ramp. But if it's negative, it'll actually mean it accelerates. No, sorry, other way around. I defined x as down the ramp. So if this is a positive number, the acceleration will be down the ramp. If it's a negative number, it'll be up the ramp. Either way, I'm going to have to divide both sides by the mass to isolate for acceleration. Okay, so I'll fill in the values now. Well, I don't have the mass, but it does cancel out. So I got a mass in the denominator, and I've got a mass in each of the terms in the numerator, so it actually does cancel out. If there's only mass in one of the terms in the numerator, then we'd be in trouble. Okay, so I'll fill in starting at g. So 9.8 sine of the angle, 60 degrees, minus mu, which is 0.28. G, 9.8 cosine of the angle, 60 degrees. Divided by 1 now, since I've canceled out the mass. So that big expression is what I throw into my calculator. I could have factored out the g, I guess, but not too big of a deal. So I end up with a positive value here. I'm ending up with 7.1. And it's positive, so that means it's going down the ramp. You don't really have to write that down because at the top right there, I defined my positive direction. In a problem set, you would write it down because you want to be really detailed in a problem set. All right, so that is acceleration down a ramp when there is friction.